Okay, so up till now, really the entirety of the course has been about following little individual particles, little blobs of mass around. So we had Newton's laws of motion, which were really what was the first thing we did when we had a free body diagram. We drew it as a point, and that's okay. I mean, it works out right, so it's not wrong. Um, but we want to be able to talk about extended shapes and things. And this is ultimately going to lead to a discussion of torque and rotations and tires and wheels and whatever. Um, Now, in principle, if you could keep track of every atom, you could use the rules that we've already discussed and just apply them one at a time over and over and over, and it would work. The problem with that is clearly that's not practical. So what we need to do is kind of develop some concepts, the concepts of, I guess, continuum mechanics to describe extended shapes, and it's going to lead to concepts like density and uh, yeah. Um, so we just need to kind of enlarge our toolbox slightly. This is a little bit more math than some of you have had. There are integrals involved, and in general, you have to do Calc 3, kind of or double and triple integrals. None of the problems we would ever do actually require that. What's going to happen is basically I'm going to work out one-dimensional examples when we need to, just to show how it would work. And then for the 2 and 3D shapes, we will just have a table of values if you needed to know the results. Excuse me. But that being said, I'm going to write it down in pretty full generality. And the reason is that this language that we're going to use is the language that will be used all through thermodynamics when we talk about intensive and extensive quantities, and also all the way through statics and dynamics and strength of materials, and through physics 2 with electricity and magnetism. We'll talk about charges spread out over space, and we'll have a charge density. And so many of these concepts work there. So if you want, some of the stuff is kind of formal, and think of it as just culture that's setting the foundation so that when you see the same basic ideas in about 2 or 3 more courses over and over and over, we're just trying to get things rolling now. The actual examples you'd ever have to do are pretty simple. Okay, so what I want to do is first imagine you have many different little blobs of mass. Okay, so you could say you have mass 1, mass 2, mass 3, mass 4, lots and lots and lots of masses, all the way up to mass n, where n is some huge number. Now, let's say we wanted to come up with a formula for the total mass. Well, that wouldn't be hard. You would just say, okay, mass total, just call it m or m total. That's just, well, it would just be the sum of all the small masses. Well, let me write it out once here. So it would be m1 plus m2 plus m3 plus all the way up to mn. Or, because that's a pain in the neck to write out every time, we could use a summation notation. We could say that's the sum over I from 1 to n of the mass of m sub I. Okay? And that would work if you had a discrete set of masses. You would just add up their individual masses, and that's what you would get. The problem comes when instead of a discrete set of masses, we have a blob of mass, sort of even just spread out all throughout this volume. And well, how can we kind of use this to motivate our steps? So basically, what we're going to do is play Legos. So whenever you have a continuous distribution of stuff, charge, mass, energy, enthalpy, entropy, doesn't matter, you can basically break the three-dimensional shape into little Legos. Okay, so break it up. Think of it as being made of a whole bunch of little Legos. Each one is going to be tiny, because in the end, we're going to take it, the limit is you get an infinite number of Legos. So basically, then you can apply this simple add them up idea, but you want to add up the masses of each Lego piece and take the limit as you have more and more and more of them. Well, when you add up more and more and more things, and as you take the limit, the Legos themselves individually get really small, so they become of differential size, infinitesimal things, and you have an infinite number of them. This sum formula becomes an integral. So that's the idea. So the idea is, instead of this sum, what we are going to do is think of these guys as each having a tiny mass. Each one has a mass that's, we'll just call it dm, or like a differential for like baby step, is the mass of each one. And then when we add them all up, that becomes the following integral. We say that the total mass is the integral over all the little differential bits of mass, all the little teeny tiny Lego pieces. And that's our formula. That's our main formula. This is true. This is a physics formula. This is not necessarily something that a mathematician, or that you learn about in math class. In math class, for the most part, you do integrals over geometry, not mass. You could, but that's not typically how it's done. And usually we like to think about geometry. It's easier for us to estimate geometry than to estimate mass, just at a sight, at a glance. And so what we want to do is turn this integral over, or sum over masses, into a sum over geometry. To do that, we're basically going to convert mass into geometry. The way we do that is the following. Well, one way to think of it is we use the chain rule. And we say that the integral over mass becomes the integral, becomes dv for volume, dv. And roughly speaking, if we're pretending differentials are fractions, the differentials just cancel, which gets us to where we want, whether or not that logic is quite right. Okay? This quantity in parentheses is called the mass density. For volume, and specifically this is the volume mass density. The symbol for density is rho. You've seen that symbol before. It's dm dv, and it's the mass density. Or it's really the volume mass density. Now, many of you, maybe from chemistry class, you learned that density was mass over volume. Not really. It's really defined with a derivative. It's the rate of change of mass with the rate of change of volume. But it turns out that if the density is constant, then you can just think of it as m over v. But that's only true if the density is constant. You could imagine that the density is different. You could imagine that the cubes over here are made of lead, whereas the cubes over here are made of feathers. I don't know. They have 3D printers where you can change the materials as you move around in your volume, and each little blob has a different mass. So the density varies as you move around. And when the density varies, you can't just say density is mass over volume. You have to use this formula. What you can think of it as is as the rate of change of mass as you increase the volume. So it's saying if you just add one more Lego piece, basically, what's the rate of change in the total mass as you add in one more Lego piece? Okay. Rewriting this, sometimes this is useful. People say that dm equals rho times dv. And so what happens is, using a density, you can turn physical things into geometry things. So physics would be mass, can be turned into geometry. Okay. So that's how that would work in principle. Now, integrating over volumes is not something most of you are used to. That's a Calc 3 concept. So we're not going to do that. We're not going to do examples with that. It involves things called double and triple integrals in all but the simplest of cases. But the idea is intuitively clear. It's just the mechanics of doing the calculus is kind of complicated. We can play the same exact game in 1 or 2 dimensions. Let's look at let's look at a 1-dimensional example. So let's say I have a 1-dimensional shape. So it's just some bendy curve. And what you can do is think of it as being broken into little line segments. And each little line segment has a tiny mass. So what we would say, just so we are clear, the size of a little line segment is given by the arc length, ds. Okay. So hopefully that, for those of you in Calc 2, that should be something you're learning about. ds is the arc length along the curve. And what you can think of then is that the mass is always going to be given by this formula. That's true. The total mass is the sum of all the little masses. That's all that says. But you can write that as the integral, and not a rate of change with respect to volume, but because the segment, or the intervals, or the little bits we're adding are lengths, we want to do that ds. And this quantity right here is called the linear charge, or linear mass density. Now, this isn't linear, but it's 1-dimensional, and that's what they're getting at. So we would define lambda to be the linear mass density. And it equals dm ds. Okay, so let's do an example to kind of see how this would play out. And then I'll come back to the 2-dimensional case afterwards. I'll just throw that in for completeness. We won't actually do examples with that in this course. Okay, so let's imagine something simple. Let's imagine I have a stick, which I will take to be 1-dimensional, just a line, and it's along, say, the x-axis. And let's assume that lambda equals 10 grams per centimeter. And let's say that the total length is 1 meter. Okay. Well, what's the total mass? Well, if the density, if it's a constant 10 grams per centimeter, and the total length is 100 centimeters, the total mass is going to be 100 times 10. It's going to be 1,000 grams. It's going to be a kilogram. Let's see how that comes out of the calculus. I would say that the mass is the integral dm. I usually start with a statement which is always true. M is equal to integral dm. And then I would turn it into a calculus statement that I can work with, and that's going to be lambda ds. But because it's along the x-axis, ds is nothing other than dx. We'll say that runs from 0 to 100 centimeters. And then that equals the integral from 0 to 100 centimeters of lambda, which was 10 grams per centimeter, dx. And the answer comes out to be 10 grams per centimeter times 100 centimeters. 1 kilogram, as advertised, 1,000 grams. Okay? That's kind of typical of how you would use these formulas. Let's do one more example. Let's imagine that rather than having something mass evenly spread out, you could imagine, I don't know, that when you made the meter stick, one end, or sorry, not meter stick, when you made this stick, somehow you had more mass on one end and almost no mass on the other end. So yeah, I don't know. The machine didn't make a good stick, I suppose. So let's imagine that lambda is given with a variable formula. It's now a function of x. And we'll say it's equal to 10 grams per centimeter squared times x, where x is in centimeters. Then I work out the formula for the mass. It would be the integral. And incidentally, it's not so easy just to guess the answer because the density is changing. It's like you've got when x is 0 over here and x equals 100 over here. Basically, there's no mass over here and there's a lot of mass over there. So what we need to do is perform an integral to calculate the total mass. That's the integral dm, which equals the integral of lambda dx, which equals the integral of 10 grams per centimeter squared times x dx from x equals 0 to x equals 100 centimeters. So this is going to be it's going to be 10 grams per centimeter squared. Don't worry, the units look funny because I had to multiply by something with units, but this overall lambda is units of mass per length. Okay, and I do the integral, so I'm going to get an x squared over 2. So when I plug in x equals 100 minus what I get when I plug in x equals 0, I'm going to get the mass equals 10 times 100 squared, and it'll come out in grams. So that's going to be 100 squared is 10,000. So I'm going to have 100,000 grams. It's going to be 100 kilograms. Hopefully I did all that right in my head. Okay, so that's how we use mass densities and that are constant or variable. The fundamental formulas are always the same. And then where the details start to matter is when you go to actually plug in and evaluate the formulas. Okay, so we've done linear things, we've done volume things. Those are the most familiar to most people. Let's talk about two-dimensional surfaces. So if we have a two-dimensional surface, it's really the same game, but instead of doing cubes or lines, we're going to imagine covering this area with little postage stamps. And each little postage stamp is going to have a little area, call it a differential area, dA. And we're going to say is that the mass equals the integral of dm. Again, that's always true. But we're going to write that as the integral of dm over dA, where dA is the area of a little postage stamp times dA. And we're going to call this thing in parentheses sigma. It's going to be the surface mass density. And it equals dm over dA. Okay. So we're not going to do an example with that, but that's how the game would be played. It's really the same Lego idea. So that's kind of an introduction to something called continuum mechanics, where you just don't follow individual particles, but you kind of smear it out into a blob. And the price you pay for that simplicity is that you introduce these new density functions that you have to manage somehow. Okay, so this is our first video in extended objects. In the next, I'm going to stop here for this one. In the next video, I'm going to use these ideas to describe center of mass and then something called the moment of inertia. After we've done that, we will kind of go back to the world of physics and use these concepts to describe extended objects that move and rotate in space.